Hi again. This is the second video in a series introducing some fundamental tools and concepts for counting complex arrangements. In the previous video, we learned how to count two different looking collections of objects, the collection of all subsets of a finite set having n elements, and the collection of all n-bit strings. And we learned that the number of such objects is 2 to the nth power for both collections, and this was no coincidence, since there was a bijection between the two sets that identifies each element of one collection as an element of the other. In this video, we're going to look at a similar but different problem, counting the number of subsets of an n-element set that have exactly k elements. We're going to see that there's a wrong way to count this collection and a right way. And the right way is going to introduce an important new idea for us. First of all, here's what we mean by k-element subsets of an n-element set. For example, we might want all the 3-element subsets of a 5-element set. We learned last time that there are 2 to the 5th, or 32, subsets of a set with 5 elements. To really see these subsets and start to detect patterns in how they're built, I encourage you right now to stop the video and just try writing out all 32 subsets of the set 1, 2, 3, 4, 5. Go ahead, try it. Okay, so if you found all of them, you should be looking at this list. Of those 32 subsets, you can see that just 10 of them have 3 elements. So the number of 3-element subsets of a 5-element set is 10. The number of 4-element subsets of a 5-element set is 5, and so on. So how would we count the number of 3-element subsets of a 5-element set other than by enumerating them, that is, by listing them and just counting on our fingers? We need some kind of algorithm for doing this in case we need to count a collection so large that enumeration is impractical, like counting the number of 100-element subsets of a 1,000-element set. So here's a well-intentioned but wrong way to do this. We begin by creating a generic 3-element subset and leave 3 blanks where the elements should go. Since there are 5 elements in the main set, there are 5 ways to fill the first blank, then 4 ways to fill the second blank because repetitions aren't allowed in sets, then 3 ways to fill the third one. Since that's a sequence of tasks, we multiply 5 times 4 times 3 to get 60 possible ways to form those sets. This sounds good at first because it's a similar counting process to how we counted the number of subsets of a set total and the number of n-bit strings in the first video, but it's wrong on 2 counts. First of all, the number of 3-element subsets can't possibly be 60 because there's only 32 possible subsets of any size for this 5-element set. So this number 60 is just impossibly large. And second, the reason that it's so large is that we've counted many subsets more than once. For example, in this sequence of choices approach I just outlined, I could choose the number 1 for the first slot, the number 2 for the second, and the number 3 for the third slot and get the set 1, 2, 3. Or I could have chosen the number 2 for the first slot, 1 for the second, and 3 for the third and gotten the set 2, 1, 3. Now obviously those are the same set because the ordering of elements doesn't matter, but my counting process counts them as different outcomes. So when I counted 60 subsets, that number 60 included a lot of duplicates that are only superficially different but are actually the same. There are 6 versions of that one subset 1, 2, 3 that are counted separately. In fact, the wrong way method, in that method, every possible rearrangement of a 3-element set is counted separately. So let's solve a different counting problem. How many possible rearrangements of a 3-element set are there? We could do it this way. Start with a blank 3-element set. There are 3 choices for the first blank, 2 for the second, and 1 for the third. Since that's a sequence of choices, we can multiply the possibilities and see that there are 6 possible rearrangements of elements in any 3-element set. So that count of 60 is off by a factor of 6, since every time a 3-element subset of 1, 2, 3, 4, 5 is chosen in this way, the wrong way method counts it 6 times. So we can actually redeem the wrong way method by taking that outcome of 60 and dividing by 6. And when we do, that's the 10 that we counted just by enumeration. So later in this series, we're going to have a more efficient way of counting these k-element subsets. But just to illustrate the concept once again, let's count a collection of subsets that would be pretty hard to do by listing all the objects. The number of 4-element subsets of a 10-element set. There are 2 to the 10th, or 1024 subsets of a 10-element set. And I really don't feel like listing all of those out. So let's start with the wrong way method and set up a generic 4-element subset by listing 4 blanks. There are 10 ways to fill in the first blank according to the wrong way method, 9 for the second, 8 for the third, 7 for the fourth, for a total of 5,040 ways to fill in the blanks. Of course, again, this is wrong because it can't be right. There are only 1,024 subsets possible, and it's too big because when we count one 4-element subset, we're actually counting all possible rearrangements of that subset separately. So, how many such rearrangements are there? Given a 4-element subset, there are 4 choices for the first blank, 3 for the second, 2 for the third, and just 1 remaining for the last one. So that's 4 times 3 times 2 times 1, which is 24 possible rearrangements. That means my wrong way count of 5,040 was 24 times too large. So the real number of 4-element subsets is 5,040 divided by 24, which is 210 of them. So in this video, we've learned that counting the number of k-element subsets of an n-element set is not just a straightforward application of the multiplicative rule, because we end up overcounting our objects. Always be careful about whether a counting algorithm counts objects more than once. But we also saw that we can determine by just how much we overcounted, and we can correct this wrong count by dividing off that factor. Thanks for watching.